Welcome back, everyone. I hope you all enjoyed the break. On behalf of Team IGT, my name is Ryan Holquist, Electrical Engineering, alongside Sean Kramer, Computer, and David Delgado, Electrical. So, we're fortunate to be going after the other two digital twins projects, General Dynamics and Acumetrics. So I'm just going to quickly review the important parts to us about a digital twin, to our capstone sponsor, IGT. That is the ability to have a digital representation of a physical device, the ability to remotely monitor this asset, using sensors integrated into the device, and the ability to use that data to create a predictive maintenance engine. Now, a little bit about the company. IGT is the world leader in end-to-end gaming solutions. That means they can go to your jurisdiction and provide as little as the hardware or the software, or all the way up to actually running the lottery itself in addition to the hardware and software, which is what they do in Rhode Island. And you might recognize some of these terminals, some of these devices on the screen here. The one on the left is a point-of-sale device. You'd probably recognize it from a gas station or a convenience store. The one in the middle is something you would see at like a grocery store or a bar, and the one on the right is actually custom designed for Walmart. And moving forward to what these devices actually do, these TouchPoint terminals, they process online wagers. That means you put in your Powerball numbers, it takes a record of it, sends it to a database somewhere, and spits out, gives you your ticket back out. And contracts with these devices can now last up to 20 years. And so the likelihood of some sort of failure is kind of high. And that's not an indictment on the device itself, but rather just a reality of the business. And when you consider that IGT has over 500,000 of these terminals worldwide and over 2 million total devices, the potential savings are immense. It doesn't take any complicated math to figure that out. And this leads to our anticipated best outcome, which is a fully functional digital twin which can make use of telemetry currently being collected, as well as that from new sensors we will be adding, and use that to establish a predictive maintenance engine. Now a little bit about the terminal that we have ourselves. We have a few views here, but the one that's really important to us is that one in the middle. That device is circled in red, in the red square is the play slip reader. What that does is it takes a play slip, inputs it, reads what's on it, and spits it back out. If you don't know what a play slip is, just come by our booth after. We'll be able to show you one. I'm sure you've seen one before. And what happens is, after long-term use, the play slip reader gets rather dirty. People have oil on their fingers and dirt, and it gunks up the motors. Or not the motors nowadays, these rollers attached to the motor that push the play slip through, and they get very dirty. And this leads to our hypothesis, which is that when these rollers get dirty, it will cause when these rollers get dirty, the motors will consume more current, and that will lead to a possible failure event. And a related event is that when the rollers are dirty, they will vibrate differently. If you imagine an off-balance washing machine, it's kind of a similar idea, but on a smaller scale and a much shorter duration of time. Now, this is proof of our first hypothesis. We need to figure out a way to simulate a dirty play slip reader. Since we didn't have one due to the way the terminals are maintained, we have to wait until one comes in to be able to get it. So we had to find a way to simulate that in the meantime. What we did was we took those play slips I was talking about earlier and just put varying numbers of them through. And as you can see, when there are 6 slips through, which is about the max we can get before the terminal starts to reject them, there's a significant rise in the current consumed by it. This seems to prove our hypothesis. And if you can imagine why 6 would be the maximum we could fit in there, is the margins in that play slip reader are razor thin. The tension is actually held on the rollers by springs, so there's really not too much room in there. Now this is the vibration sensor we're using. It's mounted there at the top, and it's attached to the back of the play slip reader. So what it does is when the reader's active, we can measure the waveform of the vibration. It actually looks a little different from this now. What we did was we shortened it to reduce the noise. And what I mean by that is, if you picture a diving board, a longer one is going to have much more movement at its tip as opposed to a shorter one. So by reducing the length of it, we can reduce that noise and get more accurate data. Now I'm going to pass it off to Sean, who's going to talk about the actual collection of this data.
Thank you, Ryan. Now that we've explained how we were able to mount the sensors to the terminal, I need to explain how we were able to grab the data from these sensors and get it to the terminal so it could be processed before being sent to the back end for our digital twin. Now, the raw data that's collected by the sensors is passed to our Arduino Nano board. The reason we selected the Arduino Nano board is because it offers USB serial communication. So the sensor data then flows from the Arduino Nano board to the terminal via that USB serial connection. Now, once the data is on the terminal, it will look something like this. This is actually from a current sensor that's attached to the motor on the play-slip reader. And as you can see, it peaks out sort of high here. And that's because this was from, it peaks up rather around 500 milliamps, which is much higher than the average when only one single play-slip is inserted. On average, it peaks out around 300 milliamps when only a single play-slip is inserted. This was around 5 or 6 play-slips. And the reason we did that was to simulate the resistance of the dirty rollers. And once this data is on the terminal, we can then process it and detect abnormalities such as this one, which could be alerted upon that this is probably running in a failure state. Now, every sensor in this terminal, including the ones we've added on, needs what's known as a collect-D plugin to run alongside it on the terminal. On the terminal, you write a collect-D plugin for each sensor to pull data from it periodically. This is an example of a plugin that I wrote for collect-D for the CPU temperature sensor. It pulls every 10 seconds the sensor that monitors how hot or cold your CPU is. And in this red box, you see the temperature start to rise. And that's because I started to stress test the CPU that's on the terminal. And when a device is under stress, it usually heats up, especially for a CPU. And as you see, once the test is over, it falls. Now, every single one of these sensors needs one of these plugins because collect-D is great for formatting your data and before it gets sent out to a backend for something like a digital twin like we're using for this purposes. And for more on the remaining challenges, as well as the broader implication of our project, here's David Delgado.
Thank you, Sean. So to reach our best anticipated outcome, we have a few remaining challenges. We want a predictive maintenance engine. To do that, we already did a lot of work on the hardware and software side. We need to develop necessary plugins so that the terminal could communicate with the PC. We also want to add additional sensors so that we think could help us with collecting data. IGT did tell us that they do have terminals outside, so we definitely want to look at humidity and temperature sensors as weather could come into play. We also need to refine data processing so that we could format the data we collect and so we could use it with the predictive engine. Lastly, setting up the digital twin software. We have been in talks with a couple companies, but we have nothing set in stone just yet. So kind of to wrap it up, we want a high level of software for monitoring TouchPoint terminals. IGT loses money every time a terminal is down, so they basically want to monitor terminals from one location and get real-time diagnostics so they could begin repairing a terminal before it actually goes down. This in turn will improve the market share because they could save a lot of money and in turn invest that money back into the company. Lastly, they want to provide the most dependable terminals on the market for an edge over the competition. And we would like to thank everybody that helped us with the project so far.